Alright, let's get started with an old school topic called solving systems of linear equations. We're just going to amp it up a little bit, and during this chapter we're also going to get to inequalities, and we're also going to get to three variables. So a system of equations is two or more equations with two or more variables. Most commonly x's and y's, but you guys will be doing x, y's, and z's, any variables possible. The solution set should be written as an ordered pair, or when we get to x, y, z, ordered triples. And it must satisfy both equations, or once we get to x, y, z, it must satisfy all three equations for it to be true. Now, during this class, we are going to learn how to solve systems 5 ways: graphing, substitution, elimination, Kramer's rule, and inverse matrices. In today's lesson, we are only going to talk about the first 3. We will get to the last 2 some other time. So, there are a few algebraic ways to solve systems, and one way is using substitution. So substitution, what you need to do is you need to take one equation and you need to get it equal to one variable. So we can just subtract the 2y from the other side and have x is equal to negative 2y plus 2. Then what we could do with that is we can substitute x with negative 2y plus 2 in this second equation. So this is going to become 5 parentheses, negative 2y plus 2, minus 3y equals a negative 29. And now we have an equation that only has one variable. So we're just going to solve for that one variable. We're going to distribute and get negative 10y plus 10 minus 3y equals negative 29. That'll give us a negative 13y plus 10 equals negative 29. And then we're going to subtract 10 from both sides and get negative 13y equals negative 39, which means y is equal to 3. So that's the first part. After you get the first variable, you need to substitute it back in to that. And now we'll get x. So we'll have x is equal to negative 2 times 3 plus 2. So x is equal to a negative 6 plus 2, so x equals negative 4. And you are just about done. You have to remember you must write your solution as a solution set. So we have x comma y, so negative 4 comma 3. In the event it's not x and y, we write them in alphabetical order. Okay? So that's that for substitution. Another very popular, and I would argue in many ways is my favorite method, is elimination. This is also known as linear combination. So what we're going to do here is you need to get one variable to disappear. So what you need is equal but opposite coefficients in front of one of your variables. So what we can do is we can actually multiply the first one by a negative 2 to get rid of our 6a. So if we multiply 3 by a negative 2, we'll get a negative 6. So we multiply everything by negative 2. That's going to give us negative 6a minus 8b is equal to a negative 20. Uh-oh, something weird is about to happen, I think. 6a minus 6a goes away. 8b minus 8b goes away. Oh no, we have nothing on the left. And 20 minus, oh my goodness, everything is gone. So, think back to solving an equation. Whenever you had your variable disappear, you had all real numbers. But now we have a system where we have two variables. If you can somehow make both variables disappear, and you are left with a true statement, then we have infinite solutions. Not all real numbers. It's infinite solutions because now we need ordered pairs. And that is because we have the same line. If we were to graph both of those lines, you would just see them stack right on top of one another. Okay, you would get the first line that would look a little bit like this, and then you'd graph the second line and it would be right on top of it. So you have an infinite number of solution sets, aka coordinates. So that's why if everything disappears and you have a true statement, you have infinite solutions. Okay, let's do the next one. Why don't you do the next one? Pause the video, give it a try. So it looks like we should be multiplying this top one by a negative 3. That gives us negative 6x minus 9y is equal to a negative 45. And then that's going to, we're going to have nothing on the left and a negative 35 on the right. And again, our variables disappeared, so this is false. And that's going to be no solution this time, because these are parallel lines. If we were to graph both of these lines, you would have a little something that looks like this. We would have the first one, and then you'd have another one, and they'd be running parallel to one another, which means they're never going to intersect, which means they have no solution. Now, not all elimination problems are going to be either infinite solution or no solution. You can get solutions. This is just for the purpose of seeing multiple different types of answers that you can get with systems. Okay, so number 4. So we have 3 equations here, but we only have 2 variables. So you would think this is going to be more complicated to solve, but really it isn't. Because you only need to solve for x and y, you only need to pick 2 equations to work with for the moment. So let's just take the bottom 2. It says solve using any method, so any method that you want to use, go for it. I, of course, mentioned that I love elimination. Why? I don't know. I don't really have a reason. This is negative 2x plus 8y is equal to a negative 18. So I'm going to use that with the one above. My x's are going to cancel. 3y plus 8y is 11y. And 7 minus 18 is equal to negative 11. So that's going to mean y equals a negative 1. So then we're going to take our negative 1 and plug it back into one of our original equations. So I'll just substitute it back into this guy. So that's going to give us 2x plus 3 times a negative 1, which is equal to 7. So that's 2x is equal to 10. So x equals 5. So we have our solution set. X is 5 and y is negative 1. But since this is a system with 3 equations, remember what the top said. The solution set must be true for all equations. So you need to go back and check it in this one. So this is going to be 3 times 5 minus a negative 1, which is equal to 5. Is 16 equal to 5? No, it isn't. So this is actually no solution again. Even though we have this, it does not work for all 3 parts of the system. So it does not work. Number 5. This one's a little tricky. When you look at this, do you really want to try to solve this system with variables in the denominator? I don't think so. So what you could do is you can create 2 new variables. Let's say a is equal to the reciprocal of x, and let's call b the reciprocal of y. What you just did right there is you just changed this to 2a minus 5b is equal to 5. And this one just got switched to 3a plus 10b is equal to 18. The only thing we did is we took the reciprocal of the x and y. Now we just solve it like a system. So we can multiply the top one by 2. And that'll give us 4a minus 10b is equal to 10. And this is going to go away. So we're going to have 7a is equal to 28. So a equals 4. Now we're going to take the a equals 4 and we're going to substitute it back into one of our original equations that we modified with a's, because that'll just make it easier. So then we're just going to have 2 times 4 minus 5b is equal to 5. And then we're just going to solve for b. And we're going to end up getting b is 3/5. So a comma b is 4 comma 3/5. But we are originally solving for x comma y. So you have to make sure you flip both of them. And our final answer is 1/4 comma 5/3. This is the one we want. This is our a and b. But remember, the original problem was x and y. So you need to start or solve for x and y. Okay? We're going to take a break here for a second, and then we are going to solve by graphing.